In mid-2025, a collective of physicists managed to assemble an instrument that slices a single second into parts so thin they defy the human vocabulary of scale. This machine calculates the passage of existence down to the 19th decimal place. To give that a baseline, the previous pinnacle of human engineering stopped at the 18th decimal place, a metric that already seemed like an exercise in cosmic over-engineering. If you let that 18th decimal clock run since the exact microsecond of the Big Bang, it would not have lost or gained a single tick. Yet we pushed further. We demanded a 19th digit. And the moment the displays flickered to life with that new tier of resolution, the universe stopped looking like a gallery of eternal statues and began to look like shifting sand. We begin with an absolute number, a digital boundary line drawn in a clean room at the National Institute of Standards and Technology. The silent crisis that this breakthrough brought to light isn't about the clock itself. It's about what the clock is measuring against. For centuries, the entire enterprise of physics has been built on a quiet foundational faith that the universe has constants. Fine structure constants, gravitational coefficients, the fundamental numerical values that hold the scaffolding of atoms together. We call them constants because we assume they are the bedrock. But when you look through a lens ground to 19 decimal places, the bedrock seems to have a pulse. The numbers appear to be drifting. It is a slow, agonizingly minute variation, but it is there. We constructed the most uncompromisingly precise diagnostic tool in the history of our species, and its very first diagnostic report suggests that the rules of the game might be changing while we play. This forces us into an uncomfortable corner before we even unpack the mathematics. We have to confront the central, circular ghost that haunts every laboratory on Earth. What are we actually tracking when we watch a clock? We understand the mechanics explicitly. We can discuss the behavior of lasers pinning strontium atoms in place, the predictable oscillations of cesium, or the rhythmic swing of a brass weight. But those are mechanisms of capture, not the thing being captured. When you look down at the glass face on your wrist, you are participating in an ancient, unexamined assumption. You believe you are tapping into an objective, independent river that flows from a distant past into an unwritten future, moving at an identical pace, whether you are awake, asleep, or non-existent. Yet, if you demand a definition of this river from the grand architecture of physics, you find a void. Every equation that features the variable of time either uses the concept to define itself or falls back on poetic tautologies dressed up in mathematical notation. Sir Isaac Newton bypassed the problem by decreeing it absolute, an empty, unalterable background stage upon which the drama of matter takes place, flowing uniformly without relation to anything external. Albert Einstein tore that stage down in 1905, proving that the stage itself warps and stretches depending on who is watching and how fast they are moving. But notice the bait and switch. Einstein didn't define what time is. He merely gave us an exquisite map of its elasticity. He told us how it stretches, how it bunches up around mass, and how it weaves into the geometry of space. As the theoretical physicist Carlo Rovelli has spent a career pointing out, our mastery over the behavior of time has masked our total ignorance of its identity. We are like mechanics who can tune an engine to flawless performance without having any idea what fuel is burning inside the block. And that specific vulnerability, that vast canyon between knowing how a thing behaves and knowing what it fundamentally is precisely where our finest instruments have started to tear holes in the script. Consider the baseline tremor that started this collapse back in 1971. It didn't require a multi-billion-dollar particle accelerator or a deep space telescope. It required two men, Joseph Halfilly and Richard Keating, 4 commercial cesium atomic clocks, and a few standard airline tickets. They didn't charter a specialized research vessel. They boarded ordinary commercial flights, flew around the world, and then compared their airborne clocks to the twin instruments that had remained completely undisturbed on the tarmac. When the planes landed, the clocks were no longer in agreement. They weren't broken. They hadn't suffered from the turbulence or the cabin pressure or the quality of aviation fuel. They had simply lived through a different quantity of existence. The clocks that had circled the globe returned home having recorded fewer nanoseconds than their stationary twins, tracking with almost terrifying accuracy the mathematical predictions laid down by Einstein decades earlier. But while the scientific community checked the boxes for relativity and moved on, a deeper, more existential realization was left hanging in the air. If two identical, perfectly functioning instruments can start at the same point in space, part ways, reunite, and report two entirely different quantities of elapsed reality, then the idea of a universal now is a psychological hallucination. There is no grand-grandfather clock ticking away in the foyer of the cosmos. There is no master ledger keeping track of the universe's age. Instead, reality is a chaotic, fractured mosaic of local timelines. Every rock, every individual human being, every drifting cloud of interstellar dust possesses its own private clock, running at a speed dictated entirely by its local speed and its proximity to gravity. We tend to categorize this as abstract physics, something reserved for black holes and science fiction. But this temporal fragmentation is already woven into the concrete infrastructure of the modern world. Every time you open a map on your smartphone to find a coffee shop, you are actively exploiting the fact that time is a fractured medium. The global positioning system relies on a constellation of satellites orbiting 20,000 kilometers above the planet. Down here on the surface, we sit deep within Earth's gravitational well and move relatively slowly. Up there, the satellites move at thousands of kilometers per hour and experience a significantly weaker gravitational pull. Because of these twin factors, the atomic clocks inside those satellites tick faster than the clocks on the ground by roughly 38 microseconds every single day. 38 microseconds is a ghost of an interval. It occurs and vanishes long before a single neuron in your brain can fire. But the math of triangulation is so violently sensitive that if software engineers did not manually inject a relativity correction into the code, if they pretended that time moved at the same rate up there as it does down here, your phone's location tracking would drift by about 11 kilometers every 24 hours. Within half a day, the entire global transit network would collapse into uselessness. The engineers didn't wait for philosophers to resolve the nature of existence. They simply adjusted for the distortion because the distortion is a brutal physical reality. But if the GPS example shows us that time distorts across thousands of kilometers, an experiment conducted at the Joint Institute for Laboratory Astrophysics in Colorado brought that distortion down to a scale that is genuinely dizzying. In 2021, researchers there aimed their instruments at a tiny cloud of ultra-cold atoms and measured the difference in the flow of time between two layers separated by a single millimeter. Not the distance between the Earth and the upper atmosphere, the width of a single credit card. The results were unequivocal. The atoms at the top of that millimeter-tall sample aged faster than the atoms at the bottom. The precision required to catch the universe in this act was an astonishing 7.6 times 10 to the power of negative 21. What this means outside the laboratory is that you do not exist within a uniform stream of time, even within the boundaries of your own skeletal frame. Right now, your brain is aging at a fractionally faster rate than your feet. Your heart is moving through a different temporal current than the shoes on your feet. The gradient is too minuscule for our blunt biological senses to register over a human lifespan, but it is a concrete, measured fact of nature. And this is where the ground begins to give way. If time is so pathologically sensitive that it alters its stride across the thickness of a single millimeter, then the word time ceases to mean what we think it means. Are we measuring a singular objective fabric of reality, or are we just using a single umbrella term to describe a chaotic collection of localized transactional relationship rates? If it's the latter, if time is merely a localized accounting trick, then what does it actually mean to say the universe has a history? How can we say the universe is 13.8 billion years old if the very concept of an age depends entirely on which millimeter of the cosmos you happen to spend those billions of years inhabiting? This crisis becomes even more acute when you turn the pages of our fundamental textbooks and realize that the direction of time is entirely missing from the core equations of physics. If you examine Sir Isaac Newton's laws of motion, James Clerk Maxwell's descriptions of electromagnetism, the strange calculus of quantum mechanics, or the field equations of general relativity, you will find a strange symmetric feature. They do not care about direction. If you replace the variable, the mathematics remains flawless. The equations describe a universe where an egg unbreaking and rising back into a hand is just as valid as an egg falling and shattering on the floor. The fundamental laws of nature are entirely blind to the difference between yesterday and tomorrow. This paradox nearly unmade the Austrian physicist Ludwig Boltzmann in the late 19th century. He looked at a world where the arrow of time is absolute, where we grow old, where wood burns to ash, where memories only look backward, and realized that the individual atoms responsible for these events have no such bias. He eventually proposed that the arrow of time is not a fundamental law of physics at all, but an illusion born of statistics. The universe, by some bizarre, unexplained cosmic fortuity, began in a state of extreme order and low entropy. Think of it as a pristine, perfectly stacked tower of cards. There is only one way for the cards to be perfectly stacked, but there are trillions of ways for them to fall into a chaotic pile. The line we call time is not an objective current. It is simply the statistical probability of a system moving from a highly unlikely state of order to a highly likely state of disorder. We don't move forward through time because of a cosmic law. We move forward because there are simply more ways for things to go wrong than for things to stay the same. Yet this statistical salvation leaves a massive unanswered debt. Why did the universe start in that impossibly orderly state to begin with? Who stacked the cards? If you remove that highly improbable starting condition, the arrow of time vanishes instantly. Every experience you have of duration, the sensation of waiting, the permanence of regret, the steady decay of your physical body is entirely downstream of an unexplained statistical fluke that occurred at the birth of the cosmos. If this arrow is truly an artifact of large-scale statistics rather than a fundamental property of matter, then if we zoom into the smallest scales down to the quantum realm where individual particles live, the arrow should begin to dissolve. And that is exactly what researchers at the University of Surrey discovered in early 2025. They were studying open quantum systems, subatomic particles that are not isolated in a theoretical vacuum, but are actively interacting with their surroundings. They wanted to see if the arrow of time would naturally emerge from the way information and energy leak out into the wider environment. What they found surprised them. Even after accounting for the messy dissipation of energy, the mathematical core of the system, the memory kernel that dictates how the past influences the present, remained perfectly symmetric. The forward trajectory was indistinguishable from the backward trajectory. The arrow of time was not bubbling up from the quantum foundation of reality. It was completely absent from the underlying equations. The direction we experience must be coming from somewhere else, sitting high above the mechanical operations of the universe. And the primary suspect for that external source is the entity doing the looking, the observer. To understand how an act of looking can manufacture a direction for time, we have to look back at a profound truth established by Rolf Landauer at IBM in 1961. Landauer demonstrated that information is not an abstract, disembodied concept. It is physical. Every time you delete a bit of data from a computer memory, forcing a microscopic switch to flip from a state of uncertainty to a state of zero, you must pay a mandatory thermodynamic fine. You must release a tiny, irreducible amount of heat into the world. This isn't due to poor engineering or cheap wiring. It is a fundamental law of thermodynamics. Processing information costs energy, and erasing information creates disorder in the surrounding air. This reality bridges information theory and the perception of time. If the arrow of time is dictated by the steady rise of entropy, and if every act of observation, every act of recording data, and every act of forming a memory is a thermodynamic event that inevitably increases entropy, then the observer cannot be viewed as a passive audience member sitting in a cosmic theater. The observer is an active engine of change. By the very act of observing the world and recording memories within your brain, you are generating heat, increasing entropy, and physically drawing the line between what you call the past and what you call the future. Memory does not merely document the passage of time. The act of remembering is the physical mechanism that helps manufacture the arrow of time. This conceptual knot was tied even tighter in late 2025 by an experimental team at Oxford University. They sought to measure the precise energy economics of timekeeping by constructing a microscopic clock using a double quantum dot, two tiny regions where a single electron could hop back and forth. Each hop represented a single tick of the world's most minimalist clock. Then they performed an audit of the energy involved. They measured how much energy it took for the electron to move naturally and compared it to the energy required by the external laboratory equipment to read the clock, to record the ticks, and to turn those subatomic movements into a coherent record. The discrepancy was astronomical. Registering the state of the clock required up to 1 billion times more energy than the actual physical operation of the clock itself, and that massive influx of measurement energy was entirely converted into entropy. When the researchers turned the measurement apparatus off and allowed the system to return to thermal equilibrium, the electron hopped left and right with completely equal probability. Without the external eye watching it, the clock had no direction. It existed in a state where past and future were entirely balanced and interchangeable. The arrow of time did not reside within the quantum dots or the electron. It materialized only when the laboratory instruments forced the system to yield a record. The direction of time was an artifact of the measurement, not a property of the object being measured. Imagine a cosmos entirely stripped of observers, stripped of recording devices, stripped of any structural matter capable of retaining information about where it has been. In such a universe, particles would still collide, fields would still ripple, and energy would still change hands. But according to the implications of the Oxford experiment, that universe would possess no arrow of time. It would exist in a perpetual, symmetric, eternal present. It would be a reality where things happen, but nothing passes. This realization aligns with a radical proposition championed by the physicist John Archibald Wheeler late in his life, the concept of it from bit. Wheeler argued that the bedrock of reality is not hard matter or flowing energy, but information, the answers to binary questions extracted by measurements. If we follow this logic to its natural conclusion, time itself is not an independent river, but a massive collective record that the universe compiles of its own interactions. But if we turn to the formal architecture of quantum mechanics to find out how it handles this parameter, we discover an astonishing act of double-dealing. In the grand synthesis of Einstein's general relativity, space and time are inseparable partners, welded together into a four-dimensional fabric called space-time that bends and deforms under the weight of stars and planets. But quantum mechanics flatly refuses this partnership. In the equations that govern the subatomic world, space is an observable, something a particle possesses, a coordinate you can measure and express as a quantum operator. Time, however, is relegated to a mere parameter. It is an external number fed into the Schrödinger equation from the outside, like a clock on a laboratory wall that exists completely independent of the experiment being conducted. Quantum mechanics, despite all its radical talk of uncertainty principles and wave function collapses, quietly smuggled Isaac Newton's absolute uniform external time back into modern physics through the back door. The entire foundation of quantum theory assumes that time flows outside the system, perfectly steady, unbothered by the quantum chaos occurring within the test tube. We have spent a century measuring quantum systems from the comfort of our position inside time, but we have never managed to measure time from inside a quantum system. In 2020, an experimental team in Vienna set out to discover what happens when you force quantum mechanics to confront its own temporal assumptions. They constructed a quantum playground designed to test the absolute law of causal order, the rule that if event A causes event B, then A must always happen first. They placed a quantum particle in a scenario where it had to undergo two separate operations, which we can call Operation A and Operation B. By exploiting the strange laws of quantum superposition, they managed to arrange the system so that the particle did not experience A then B, nor did it experience B then A. Instead, it experienced both configurations simultaneously. The particle existed in a genuine physical superposition of causal orders, A occurred before B and B occurred before A at the same time within the exact same experimental run. This was not a statistical trick or a case of missing data. The final state of the particle could only be mathematically explained if the causal sequence itself was completely indefinite. This tells us that causality, the foundational intuition that the past invariably precedes and dictates the future, is not a fundamental feature of the subatomic world. It is an emergent property that only solidifies when we zoom out to the macroscopic scale, much like the way a smooth wave emerges from the chaotic individual collisions of trillions of water molecules. At the root of reality, the universe does not possess a built-in before or after. It only develops a definite chronological sequence when an observation forces the superposition to collapse into a single, concrete record. This leaves us with a profound structural contradiction at the heart of science. We have general relativity demanding that time be a dynamic, flexible participant woven into the geometry of mass. We have quantum mechanics demanding that time be an inert, rigid, external metric that never changes its pace. Both frameworks are staggeringly successful. Both have been verified to stunning degrees of accuracy in their respective domains. Yet they speak entirely incompatible languages when it comes to the nature of duration. They cannot both be right. In 1967, John Wheeler and Bryce DeWitt attempted to resolve this deadlock by doing the most straightforward thing imaginable. They took the mathematical machinery of quantum mechanics and applied it to the universe as a whole. They didn't isolate a single electron or a single photon. They treated the entire cosmos, every star, every black hole, every atom, and every square inch of space as a single grand quantum state. When they finished the calculation and looked at the resulting formula, they found something shocking. The variable, the symbol for time that had appeared in every dynamic equation since the Renaissance, had completely vanished. The final Wheeler-DeWitt equation describes a universe that does not age, does not evolve, and does not move. From the perspective of the cosmos as a whole, reality is a frozen, static, timeless monument. Change is not written into the ledger of the total universe. This presents an obvious, almost absurd problem. If the ultimate equation of quantum gravity insists that the universe is static and timeless, why are you able to read these words? How do we reconcile a timeless cosmos with our vivid, undeniable experience of change? An answer was proposed in 1983 by the physicists Don Page and William Wooters, who suggested that time is an illusion born of perspective, specifically the perspective of being inside the system. They argued that if you look at an entangled quantum system from the outside, it will appear completely static and dead. But if you step inside that system and use one part of it to measure another part, using one photon as a clock to track the state of a second photon, time will naturally emerge from the internal quantum correlations. In 2013, an experimental team in Italy put this relational interpretation to a direct test. They created a miniature universe consisting of just two entangled photons and observed it from two radically different vantage points. First, they took the position of an external observer, looking at the two-photon system as an isolated whole from the outside. From this perspective, the system was entirely static. No change, no evolution, no passage of intervals. A perfect miniature confirmation of the timeless Wheeler-DeWitt equation. Then they changed their perspective. They placed an internal observer inside the system, using the polarization of the first photon as a clock to measure the state of the second photon. From this internal vantage point, a history materialized. The clock ticked. The second photon changed its state in response to those ticks, and an arrow of time emerged where none had existed before. The profound takeaway of this experiment is that time is not a global property of the universe. It is a local phenomenon that arises exclusively from the quantum entanglement between an observer and a clock. If you could somehow stand outside the universe, you would look at a frozen, unchanging tapestry. But you cannot stand outside the universe because there is no outside to occupy. By definition, we are internal participants, woven into the fabric of the system we are trying to observe. Our perception of time is the raw physical sensation of being an entangled part of a larger whole. This means that our ongoing pursuit to understand the universe requires us to test our maps of time to their absolute limits. As we speak, this confrontation is playing out on a global scale. High above our heads, aboard the International Space Station, the Atomic Clock Ensemble in space, ACES mission, is running a relentless gauntlet against Einstein's general relativity. It utilizes two advanced instruments, a cold atom cesium clock and a hydrogen maser, to generate a time signal of such staggering stability that it can detect fractional frequency variations down to 1 times 10 to the power of -16. The scientists managing this mission are not trying to validate Einstein yet again. They are actively searching for the exact decimal place where his description of spacetime begins to splinter. They are comparing these space-bound clocks continuously with ground-based atomic networks, searching for any tiny anomalous drift in the signal that cannot be explained by our current laws. Everyone in the community understands that general relativity and quantum mechanics must break down somewhere, and the ACES mission is designed to locate that exact structural seam. But even a tool as refined as the ACES mission faces a fundamental limitation. It can only test the smooth, geometric predictions of relativity. It cannot force relativity and quantum mechanics to show their hands simultaneously within a single unified measurement. To find the true origin of time, we need an experiment that straddles both worlds at once, an experiment that watches how a quantum wave function behaves while it sits inside a changing gravitational field. That boundary line was finally crossed in July 2025. A research team led by Igor Pikovsky at the Stevens Institute of Technology devised a way to analyze a quantum system under the simultaneous influence of both quantum superposition and gravitational time dilation. They didn't look at a massive object like a satellite, nor did they look at an isolated subatomic particle in a flat vacuum. They calculated what happens when a single particle with internal degrees of freedom, effectively a tiny single particle quantum clock, is placed into a spatial superposition where it is simultaneously closer to and further away from a source of gravity. According to relativity, the component of the particle that is closer to the gravitational source must experience time moving slower than the component that is further away. But according to quantum mechanics, these two components are entangled parts of the same single wave function. When you combine these two realities, a brand new phenomenon emerges. The gravitational time dilation forces the particle's wave function to naturally decohere. The difference in the flow of time across the particle's superposed paths acts as a natural observational mechanism, destroying the quantum interference pattern and forcing the system to choose a single classical reality. This is the missing link we have been looking for. It suggests that gravity, the very geometry of space, is actively acting as an observer on the quantum world. The reason we do not see tables, chairs, or human beings existing in quantum superpositions is not because the quantum laws stop working at our scale. It is because the Earth's gravitational field introduces a tiny, inescapable gradient in the flow of time across the volume of any object. This gradient acts as a continuous silent measurement, dissolving the quantum superpositions of the large-scale world and cementing the definite one-way classical reality we inhabit. We are left standing on a very different shore than the one we started from. We began our history believing that time was an eternal, objective river, independent of us, carrying the universe forward at an immutable pace. But our finest instruments have systematically dismantled that comfort. They have shown us that time is fractured, that it alters its stride across the width of a credit card, that its direction is an artifact of our own thermodynamic memories, and that its very existence disappears when we look at the universe as a unified whole. The 19th decimal clock at NIST did not discover a flaw in our engineering. It pulled back the curtain on a deeper truth that we are only now beginning to articulate. Time is not the framework within which the universe is built. Time is the relational currency paid by an observer who is brave enough to sit inside the system and look around. The ground beneath physics is not shifting because our theories are failing. It is shifting because we are finally building instruments precise enough to remind us that we are not spectators looking at a universe. We are pieces of the universe looking at ourselves, and time is simply the heat generated by that gaze. The realization that gravity itself might be acting as a silent universal observer brings us to a strange new plateau. For generations, we treated the quantum world and the macroscopic world as two separate countries divided by an invisible border. We assumed that the rules of the incredibly small were somehow quarantined, kept at bay by a sheer change in volume. But the work breaking through right now suggests that the border is actually maintained by the asymmetrical flow of duration itself. The cosmos isn't divided by size, it is divided by clarity. And that clarity is being enforced every single microsecond by the fact that the top of any object is moving through reality at a fractionally different pace than its base. When you look closely at this mechanism, the historical separation between matter and duration begins to dissolve entirely. We used to think of space as an empty container, and time as a ticking clock on the wall of that container, with matter acting as a tenant that moves around inside them. But if a single particle can lose its quantum properties simply because it occupies two different altitudes at once, then matter, space, and duration are not separate entities interacting with one another. They are different faces of the same underlying architecture. The presence of mass changes the rate at which duration unfolds, and that alteration in duration is precisely what we perceive as the force of gravity. You don't fall to the earth because of a magnetic-like pull. You fall to the earth because your body is naturally responding to the fact that time is moving slower at your feet than it is at your head. Your physical trajectory is an orientation toward the slower current of reality. This realization forces us to re-examine the very concept of an event. In our everyday vocabulary, an event is something that happens at a specific place and at a specific moment. It is a point on a grid. But if there is no universal grid, if every point in the cosmos is spinning out its own private thread of duration at its own private speed, then an event is not a point. It is an intersection. It is a moment where two private timelines cross and exchange information before parting ways again. The universe is not a collection of things. It is a web of these local transactions. This transactional view of reality helps clarify the bizarre results of the relational time experiments that have left traditional theorists so deeply unsettled. Remember the two photons in the laboratory that appeared completely static when viewed as a whole from the outside, but suddenly displayed a ticking clock and a sequence of changes when viewed from the inside. That isn't just a quirky paradox of quantum optics. It is a blueprint for how the entire macrocosm constructs the illusion of history. When we look out at the night sky and chart the life cycles of distant stars, or when we dig into the earth and read the ancient history of our planet, written in layers of stone, we are looking at the internal ledger of an entangled system. We are reading the correlations that have built up between the different parts of our universe because we are trapped inside it with them. The question that naturally follows is whether it is even possible to talk about an objective reality if all our measurements are inherently relational. If every clock requires an observer to register its ticks, and if every observer requires a thermodynamic expenditure of energy that actively alters the entropy of the surroundings, then the ideal of the detached scientific observer is dead. We cannot stand on a platform outside the mechanism and take clean notes. Every observation we make is a physical intervention. Every time we determine the sequence of past and future, we are acting as a piston in a cosmic heat engine, driving the very arrow of time we claim to be merely studying. This systemic entanglement becomes deeply problematic when we try to apply our current models of physics to the true extremes of nature. Consider the interior of a black hole, or the absolute first fraction of a microsecond of the Big Bang itself. These are places where our two master theories are forced to occupy the exact same coordinate. In the heart of a black hole, an immense quantity of mass is compressed into a subatomic volume. Relativity demands that the immense mass distort spacetime to an infinite degree, effectively bringing the flow of time to a dead stop. At the exact same boundary, quantum mechanics demands that the subatomic compression obey the laws of wave functions and uncertainty principles, which require a background time parameter to evolve. When you throw both sets of mathematics at the problem, the machinery catches fire. The equations produce infinities and contradictions that make it impossible to predict what actually happens. For decades, we assumed this breakdown was just a mathematical knot that could be untied if we simply discovered a more clever way to merge the formulas. We thought we were just missing a piece of the puzzle, like a unified theory of quantum gravity that would smoothly stitch the two frameworks together. But the perspective shifts entirely if the problem isn't a lack of cleverness, but a flaw in our underlying premise. What if the reason we cannot combine relativity's dynamic time and quantum mechanics' fixed time is because time itself does not exist at that level of reality? This is the radical conclusion that the Wheeler-DeWitt equation has been whispering to us since the late 1960s. It is a conclusion that a growing faction of theoretical physicists is finally beginning to take seriously. If you strip away the assumption that time is fundamental, the paradoxes of the Big Bang and black holes stop looking like brick walls and start looking like signposts. They are telling us that we have reached the edge of the illusion. Just as a single molecule of water does not possess a temperature, because temperature is merely the average kinetic energy of a massive crowd of molecules, a single fundamental building block of reality does not possess a timeline. Duration is an emergent property that only appears when you group trillions of these building blocks together and view them from a certain perspective. If time is emergent, then our entire historical narrative of the cosmos is a convenient translation rather than a literal truth. We are accustomed to thinking of the universe as a long, continuous film strip that began with a blinding flash of light and has been unspooling frame by frame ever since. But if the fundamental equations are timeless, then the film strip isn't unspooling. All the frames exist simultaneously in a vast, multidimensional landscape of possibilities. The past is not gone, the future is not waiting to happen, and the present is not a moving spotlight. Instead, every moment that could ever happen is permanently written into the geometric architecture of the whole. Our perception of moving through that landscape frame by frame is entirely a constraint of our local biology. We are creatures built out of chemical reactions that rely on the steady increase of entropy to store information. Our brains can only form a memory if they burn energy and release heat into the environment, creating a physical record of where we have just been. Because our neural architecture can only look back at the trail of disorder it leaves behind, we experience the timeless landscape as a one-way journey. We are like passengers on a train who are forced to sit facing backward, watching the landscape recede from view, while having no ability to see what lies around the bend ahead. We mistake the direction of our gaze for the direction of the tracks. This brings us back to the 19th decimal clock at the National Institute of Standards and Technology and the strange drift of the fundamental constants it detected. If the fixed numbers that govern the strengths of the forces of nature are changing, it means the landscape itself isn't completely rigid. It has a subtle, rolling contour. When we measure a drift in a constant over what we call a year, we aren't witnessing a change over time in the traditional sense. We are witnessing our own movement through a region of the timeless cosmos where the rules fluctuate fractionally from one coordinate to the next. The clock isn't catching the universe in the act of changing. It is catching us in the act of traveling across a vast, heterogeneous terrain. This shift from a temporal universe to a geometric, relational universe changes the nature of our deepest questions. We no longer need to ask how the universe began or how it will end, because those questions require a global timeline that the cosmos simply does not possess. Instead, we have to ask a much stranger question. How does our specific perspective construct the appearance of a timeline out of a timeless reality? What is it about the specific way human beings are entangled with matter that causes the world to look like a sequence of causes and effects? The answer seems to lie within the concept of quantum information theory. In recent years, researchers have begun to look at the universe not as a collection of physical particles, but as a massive network of information exchange. Every time two particles collide, they are effectively exchanging data, updating their internal states based on the properties of the other. When a particle interacts with its environment, it leaves a footprint, a tiny piece of information that registers its presence. As these interactions multiply by the trillions of trillions every second, The information becomes deeply distributed across the entire system. This distribution of information is what physicists call decoherence, and it is the true driver behind the appearance of classical reality. When a system becomes deeply decohered, its quantum superpositions vanish and its properties solidify into definite values. But here is the critical connection. The process of decoherence is completely irreversible. Once a piece of information has leaked out into a massive environment and become scattered among trillions of surrounding particles, you can never gather it back up again. It is lost to the crowd. This irreversible leakage of information is the exact physical mechanism that generates the steady rise of entropy. Therefore, the arrow of time is not a separate force driving the universe forward. It is simply the scar tissue left behind by the continuous leakage of quantum information. We perceive a direction to reality because we cannot undo the interactions that have already occurred. Every time a particle leaves a record of its existence in its surroundings, it adds a new stitch to the collective fabric of history. The past is nothing more than the sum total of all the records that have become permanently engraved into the state of the world. This brings a striking perspective to the experiments conducted at Oxford and Vienna. When those teams managed to erase the arrow of time or place causal order into a superposition, they did so by isolating tiny quantum systems so completely that information could not leak out into the environment. They created artificial pockets of reality where the universe was prevented from keeping a record of itself. And the moment the universe stopped recording, time stopped moving. The past and the future collapsed back into a symmetric, interchangeable state. The arrow of time only reappeared when the researchers opened the door to the lab and forced the system to yield its data to the outside world. What this implies is that our human existence is a continuous act of time creation. We are massive, highly organized structures designed to gather information, process it, and store it as memory. We are, by our very nature, engines of decoherence. Every breath we take, every thought we think, and every glance we cast across a room is a macroscopic intervention that forces countless quantum possibilities to collapse into a single, permanent history. We do not live inside time. We are the factories that manufacture it. This leaves us with a perspective that is both exhilarating and deeply unsettling. It means that the universe we observe is not a cold objective machine that runs independently of our presence. The grand narrative of the cosmos, the long sequence of events stretching back to the beginning of reality, is a story that requires an audience to exist at all. Without an internal observer to track the relationships between the parts, the universe would return to its true fundamental state, a vast, silent, unchanging monument of pure potential. As we look forward to the data still streaming in from the atomic clocks aboard the International Space Station and the laboratories on the ground, we have to accept that our traditional vocabulary of reality is broken. We can no longer use simple words like before, after, always, or never without acknowledging that these are local approximations, useful fictions that we use to navigate our immediate surroundings. They are the training wheels of human consciousness, designed to keep us from falling over in a reality that is far more vast and interconnected than our senses can directly handle. The 19th decimal place did not reveal a flaw in our understanding of nature. It revealed the true depth of our participation in it. We built the most precise instrument in human history to measure an independent reality, and instead, we caught a reflection of our own eyes looking back at us through the glass. The ground beneath physics is not solid because it was never meant to be solid. It is a fluid, dynamic relationship, a continuous conversation between the observer and the observed, where the single most important rule is that the story changes depending entirely on where you stand to tell it. This is the true frontier of modern science, not the conquest of an external world, but the gradual, courageous awakening to the fact that we are the ones holding the clock. The realization that we are the ones holding the clock completely reframes the historical arc of human curiosity. For thousands of years, our species looked up at the stars and assumed we were passive tenants inhabiting a cold, majestic clockwork box. We spent centuries trying to find the key to that box, trying to decipher the precise mechanics of its gears so we could predict its movements with absolute certainty. But as our modern instruments peel back the layers of reality down to the 19th decimal place, they are showing us that there is no box. There is only a vast, interconnected web of relationships, and the very concept of a gear turning in sequence is a translation that our own brains impose upon a timeless landscape. This brings us to a profound crossroad in how we conduct the enterprise of science itself. If the foundational structures of reality, the things we call mass, charge, and the constants of nature, are not immutable truths carved into the stone of the cosmos, but are instead sliding values that depend entirely on the perspective of the observer, then the traditional divide between the subjective and the objective collapses. We can no longer treat the human mind as a separate, accidental byproduct of evolution that happened to show up late to the cosmic party. The mind, or at least the physical process of observation and information processing that defines the mind, appears to be an active, structural pillar of the universe. To truly comprehend the depth of this shift, we have to look closely at what happens when a system is completely stripped of this processing power. Imagine a dead planet orbiting a dead star in a remote corner of an unobserved galaxy. There are no eyes to see the light, no instruments to log the radiation, no biological systems to store memories of the past, and no technological devices to register a coordinate. In our classical way of thinking, that planet is still moving through time. It is still aging, its rocks are still eroding, and its star is still burning through its nuclear fuel frame by frame. We assume this because we automatically project our own perspective onto the scene. We imagine ourselves standing on the surface of that dead world, watching the sunset and checking our watches. But according to the stark implications of the relational and quantum experiments of the mid-20s, that projected perspective is a lie. Without an internal system to establish a boundary, to isolate a clock, and to exchange information through an irreversible thermodynamic process, the timeline of that planet dissolves. The atoms that make up its rocks remain in a vast, sprawling cloud of quantum probabilities. The star does not burn down a linear path from past to future. It exists in a superposition of all its possible states simultaneously. It is both young and old, bright and dark, existing as a single wave function within a timeless landscape. The history of that world only solidifies into a concrete sequence of events if it interacts with something outside itself. If a stray photon from its star travels across the void and collides with the sensor of a telescope built by an observer on a completely different planet, the act of recording that photon is what retroactively reaches back through the void and forces the history of that distant star to have happened in a specific way. This retrospective creation of history is not a comfortable idea for traditional materialists, but it is an inescapable consequence of taking our most advanced measurements seriously. It suggests that the past is not a solid, unalterable track that is permanently locked away behind us. The past is a fluid network of possibilities that is continuously being pruned, shaped, and cemented by the interactions occurring in the present. We are actively writing the history of the universe by the very act of living in it. This perspective provides a radical new lens through which to view the ongoing data coming from the world's most advanced observatories. When we use our most powerful telescopes to look back at the oldest light in the cosmos, we are not just passive historians looking through a window at a distant, ancient world. We are active participants in the final step of a multi-billion-year quantum measurement. The light from those early stars has been traveling through a timeless, superposed state for eons, holding all its options open. It is only when those ancient photons finally hit our modern detectors, causing a current to flow and a digital record to be written into a database, that the quantum wave function collapses. We are, in a very real sense, finalizing the birth of the early universe from our laboratories in the present day. This loops back to the unsettling discovery made by the 19th decimal clock at the National Institute of Standards and Technology, the observation that the fundamental constants of physics might be slowly drifting. If the past is still being actively resolved by the measurements of the present, then the numbers that hold physics together should not be expected to be perfectly rigid. They are the average values of an ongoing cosmic negotiation. As the network of entanglement expands, as more of the universe interacts with itself and builds up a deeper collective memory, the background rules of the game are bound to settle into slightly different configurations. The drift caught by our finest instruments is the sound of the universe adjusting its own framework as it continues to process its own existence. This realization alters our understanding of what it means to make a measurement. In the old paradigm, a measurement was an attempt to discover a pre-existing truth. You put a thermometer in a beaker of water to find out how hot it already was. You held a ruler against a piece of wood to find out how long it already was. But in the relational universe revealed by modern physics, a measurement is an act of creation. It is the moment where two separate systems enter into a thermodynamic contract, agreeing to collapse their chaotic superpositions into a single shared reality. The thermometer does not discover the temperature. The interaction between the water and the thermometer manufactures the temperature. The clock does not discover the time. The interaction between the observer and the atomic oscillation manufactures the duration. We already have clues about how this coordination works, and they come from the study of quantum entanglement. When two particles become entangled, they lose their individual identities and become part of a single, unified quantum state. No matter how far apart you separate them, whether they are centimeters apart in a laboratory or light years apart across a galaxy, any measurement performed on one particle instantly resolves the state of the other. For decades, this phenomenon was treated as a bizarre, non-local anomaly that somehow violated the speed limit of light. Einstein famously dismissed it as spooky action at a distance because he could not reconcile it with his model of a smooth, continuous spacetime. But if you invert the problem, the spookiness vanishes. If spacetime is not a fundamental background fabric, but is instead an emergent property generated by quantum information, then entanglement is not a strange signal traveling through space. Entanglement is the thread out of which space itself is woven. Two particles do not look connected because they are sending faster than light signals across space. They look connected because they are sitting right next to each other in the true underlying informational network. And the space between them is an illusion generated by their lack of entanglement with the rest of the world. When you apply this logic to time, the perspective becomes even more profound. Just as space is the macroscopic manifestation of quantum entanglement across different coordinates, time is the macroscopic manifestation of quantum entanglement across different states. The reason you feel connected to the person you were yesterday is not because your consciousness has traveled along a continuous timeline from past to future. It is because the physical state of your brain right now is deeply quantum mechanically entangled with the records and scars left behind by the state of your brain yesterday. The line we call time is nothing more than the structural cord of information that binds these different states together. This shift from a mechanical universe to an informational one helps explain why the direction of time feels so absolute to our biological senses, even though it is entirely missing from the fundamental laws of motion. Our biological survival depends entirely on our ability to predict the immediate future based on the records of the immediate past. To do this, our bodies must operate as highly efficient thermodynamic engines, constantly consuming energy, processing environmental data, and expelling waste heat and entropy. This constant production of entropy is the price we pay for our memories. We cannot have a memory of the future because forming a record requires a mandatory increase in disorder, and the future is, by definition, the region of reality where that specific disorder has not yet been generated. The arrow of time is not a cosmic highway. It is the exhaust pipe of human consciousness. This brings a raw, existential clarity to the results of the Oxford University experiment, where reading a microscopic quantum clock cost up to 1 billion times more energy than running the clock itself. That staggering ratio isn't a design flaw that can be optimized away by future engineers. It is the literal exchange rate of reality. It tells us that the universe charges an immense premium for clarity. It costs next to nothing for things to happen in a symmetric, timeless blur of quantum potential. The electron can hop back and forth forever without consuming any real resources or generating any permanent consequences. But the moment you want to know what happened, the moment you demand a clear, unambiguous record that separates before from after, the universe demands an enormous thermodynamic tribute. It forces you to burn energy, create entropy, and permanently alter the state of the surroundings. The act of knowing is the most expensive operation in the cosmos. If the act of knowing is what drives the creation of time, then we have to confront a question that borders on the vertiginous. What happens when our systems of knowing become so precise that they begin to outrun the universe's ability to pay that thermodynamic tribute? This is the hidden wall that our technology is currently racing toward. As we push our atomic clocks to the 19th decimal place and beyond, and as we develop quantum computers that manipulate information at scales where traditional causality breaks down, we are operating at the absolute edge of the transactional matrix. We are demanding a level of historical resolution that the underlying quantum fabric is reluctant to give up. When we look at the results from Giulia Rubino's lab in Vienna, where causal order itself was placed into a superposition, we are seeing what happens when we push past that edge. By isolating a quantum particle so perfectly that it experienced two contradictory historical sequences simultaneously, the researchers essentially created a local pocket of reality that was exempted from the tax of duration. They proved that before and after are not absolute laws enforced by a cosmic authority. They are local agreements that can be suspended if you can manage the energy economics of total isolation. This suggests that our future technology will not just be about moving faster or computing more data within the framework of time. It will be about manipulating the framework of time itself. If we can master the rules of relational time, if we can understand exactly how the interaction between an observer and a clock constructs the timeline, we may learn to build systems that can operate outside the constraints of traditional sequence. We could build networks that process information not in serial or parallel, but in a superposition of causal directions, solving complex problems by allowing the effect to shape the cause just as much as the cause shapes the effect. But as we stand on the threshold of this new paradigm, there is a distinct note of humility that we must carry with us. The pursuit of the 19th decimal place was driven by an ancient Faustian desire for total control. We wanted to dominate time, to pin it down to an absolute metric so precise that nothing could ever escape our calculations. We wanted to become the absolute masters of the cosmic clockwork. Instead, the universe did what it has always done when humans push it into a corner. It broke our mirrors. It showed us that the absolute certainty we were chasing is an illusion born of our own blunt senses. It showed us that the deeper we dig into the bedrock of reality, the more we find that the bedrock is made of us. The drift of the constants, the elasticity of the millimeter, the symmetry of the quantum dot, and the timelessness of the total cosmos are all pointing toward the same inescapable truth. We are not separate intelligences studying an independent world from afar. We are the eyes and ears of the cosmos, the local focus points through which a vast, timeless reality wakes up, looks at itself, and tries to figure out what it means to exist. The next chapter of physics will not be written by ignoring this realization or trying to force it back into a Newtonian box. It will be written by leaning into the strangeness. We must learn to build a new vocabulary, a new mathematics, and a new philosophy that can handle a reality where time is a local relationship. History is a creative act, and the universe has as many timelines as it has participants. We must find the courage to let go of the idea of a solid, unchanging ground beneath our feet and learn to swim in a sea of pure, entangled potential. The clock is ticking, not because the universe demands it, but because we are still looking, still remembering, and still trying to find our way home through the landscape we are creating with every breath. This continuous loop of creation and observation reshapes our understanding of the cosmic horizon. If we accept that duration is manufactured through local partnerships of entanglement, we are forced to look at the massive structures of the cosmos not as old things that have survived a long journey through a ready-made history, but as dense nodes of high-volume information exchange. A galaxy is not merely a collection of old stars spinning in an ancient vacuum. It is a sprawling, hyper-connected library of mutual records, a place where trillions of particles are constantly reading and writing each other's coordinates, hammering out a robust, shared illusion of a stable historical trajectory. The deeper the entanglement within a system, the more solid and unyielding its timeline appears to be. This explains why the macroscopic world feels so reassuringly permanent to our daily awareness. When you look at a mountain or a stone floor, you are looking at an object that is being continuously measured by trillions of surrounding air molecules, photons, and gravitational ripples every single microsecond. The sheer volume of these environmental interactions acts as a relentless, high-powered quantum surveillance network. The mountain cannot slip into a superposition of histories or wander into a timeless blur because its environment is constantly auditing its position, forcing it to maintain a clear, unambiguous, classical state. The rigidity of our world is not an inherent property of matter. It is a statistical consensus maintained by a multi-layered bureaucracy of continuous subatomic interactions. But when we build instruments like the optical lattice clocks at the National Institute of Standards and Technology, we are intentionally breaking that consensus. We take a handful of strontium atoms, isolate them from the chaotic noise of the wider environment, suspend them in a pristine web of laser light, and cool them down to temperatures that mimic the absolute freeze of deep space. We strip away the environmental bureaucracy. We prevent the surrounding world from auditing these atoms, leaving them in a state of hyper-purified isolation. And then we do something inherently contradictory. We demand that this highly isolated system report its state to us with 19 decimal places of precision. The moment we attempt this, we are trying to eat our cake and have it too. We want the system to remain uncorrupted by environmental measurements so it can maintain its pristine quantum rhythm, but we also want to extract a high-resolution, definitive classical record from it. The slight drift in the fundamental constants captured by these instruments is the structural strain of that paradox. It is the mathematical friction that occurs when the blunt, macroscopic world of human observation tries to force its linear sequential bookkeeping onto an underlying reality that is fundamentally fluid, relational, and timeless. The numbers look like they are shifting because the act of measurement is trying to project a multidimensional landscape of quantum correlations onto a flat, one-dimensional timeline. This structural projection error is what creates the illusion of cosmic expansion and deep time. For decades, standard astrophysics has rested on the observation that distant galaxies are moving away from us, their light stretched out into longer, redder wavelengths as it travels across the void. We interpret this cosmological redshift as proof that space itself is expanding like an inflating balloon, stretching the light as it flies. From that expansion rate, we run the film strip backward and calculate that the entire cosmos must have been concentrated into a single infinitely dense point, roughly 13.8 billion years ago. But look at the deep assumptions smuggled into that calculation. It assumes that the properties of space and light are absolute, independent constants that remain perfectly uniform across the entire history of the cosmos. It assumes that a meter in the deep past meant exactly the same thing as a meter does today, and that a second ticked at an identical pace before the first stars ever collapsed out of the primordial dust. It treats the universe as a grand, objective container that has been steadily growing older on a single, universal clock. If the relational interpretation verified by modern laboratories is correct, that entire framework is an inverted reading of the data. The stretching of light from distant galaxies isn't telling us that space is physically growing larger over an objective timeline. It is telling us that the degree of quantum entanglement between us and those distant regions of the cosmos is fractionally different than the entanglement within our own local neighborhood. The redshift is a measure of informational distance, not spatial expansion. When we look out at a galaxy billions of light years away, we are looking at a system that has exchanged fewer bits of data with our local sector of the universe. Because it is less entangled with us, its relational clock runs at a different rate relative to ours. The apparent age of the universe is not a description of a historic journey that began with a physical explosion. It is a measurement of the depth of our connection to the rest of the cosmic network. This shifts the entire mission of physics away from the search for origins and toward the study of architecture. We no longer need to explain what happened before the Big Bang, because the word before has no meaning outside the local thermodynamic records generated by an observer. The Big Bang is not an event hidden away in a distant, unpromising past. It is the geometric boundary of our informational network. It is the horizon where the correlations between our local environment and the wider cosmos drop to zero. It is the edge of our map, not the beginning of our timeline. This helps make sense of the unsettling results from the atomic clock ensemble and space mission and the calculations of Pikofsky's team regarding gravitational decoherence. They are showing us that gravity is not an independent force field that pulls on matter. Gravity is the geometric manifestation of informational gradients. Where mass is dense, interactions are frequent, information leaks out rapidly into the environment, decoherence is absolute, and duration unfolds at its slowest, most stabilized pace. Where mass is scarce in the great voids between galaxies, interactions are rare, superpositions persist, and the local current of duration runs wild and untamed. Space-time is not a smooth, pre-existing canvas upon which the universe is painted. It is an irregular, fluctuating network of local transactions, a tapestry that is continuously being knit together by the exchange of quantum information. If space-time is an emergent network, then our human relationship to reality is far more intimate and influential than we have ever dared to imagine. We are not fragile biological accidents clinging to a rock that is hurtling through an indifferent mechanical void. We are highly specialized, concentrated hubs of entanglement. We are the places where the cosmos is working at its highest intensity to turn raw, symmetric quantum potential into clear historical reality. Our brains are not just passive data processors that register an external world. They are the active nodes that stabilize the local network, generating the very sequences of cause and effect that make organized life possible. This brings us to the core of the thermodynamic dilemma established by Rolf Landauer and the Oxford quantum dot experiments. If the act of knowing, the act of stabilizing reality into a sequence of clear records, costs a massive premium in energy and entropy, then consciousness is not a free passenger in the cosmos. It is a highly demanding, expensive luxury. The universe must burn through an immense amount of potential, converting pure symmetric order into chaotic, irreversible heat, just to allow a single conscious observer to register a single sequence of events. The arrow of time is the physical receipt for that transaction. Every time you remember a childhood event, every time you make a plan for tomorrow, and every time you watch the second hand sweep across your watch, you are actively signing off on that cosmic bill. You are paying for your clarity with the steady, irreversible degradation of your physical surroundings. This realization exposes a profound irony at the heart of our technological civilization. We are currently obsessed with building larger, faster, and more complex information processing systems. We are filling massive data centers with rows of servers, designing artificial intelligence models that process trillions of parameters, and constructing quantum computers that operate at the ragged edge of reality. We think we are just building tools to help us map and dominate an external world. But if Landauer's principle is an absolute law of nature, our relentless pursuit of total information resolution is actively accelerating the local decay of the universe. The more bits of data we extract, store, and manipulate, the more heat we dump into the environment, and the faster we drive the local arrow of time forward. We are like a civilization that is cutting down its own forests to build better microscopes to study the leaves. Our drive for complete decimal place certainty is a self-consuming fire. The more precisely we try to measure the world, the more chaotic and unpredictable we make its wider boundaries. This boundary wall is precisely what the physicists in Vienna ran into when they placed causal order into a superposition. By engineered isolation, they managed to cheat the thermodynamic tax of duration for a single particle, allowing it to experience A before B and B before A, simultaneously. They created a tiny oasis of total efficiency, a place where information could be processed without generating entropy or establishing a past and a future. But notice the catch. That oasis could only exist as long as it remained completely hidden from us. The moment the researchers hooked up their detectors and demanded to know the outcome, the outside world flooded into the system. The tax was collected, the superposition collapsed, and the particle was dragged back into the linear, irreversible stream of macro reality. You can have quantum freedom or you can have classical certainty, but you cannot have both at the same time. The universe maintains its books with absolute, unyielding rigor. This structural limit means that the future of human engineering will require a radical shift in philosophy. We cannot continue to build systems that rely on the brute force extraction of classical information from the quantum world. We must learn to design technologies that operate in harmony with the relational, symmetric nature of reality. We need to develop computers and instruments that can process information without forcing it to collapse into a single history, systems that can think and calculate within the fluid, timeless landscape of superposition before delivering an outcome. We must learn to become comfortable with ambiguity, recognizing that our demand for absolute pseudodecimal certainty is a symptom of a primitive mechanical mindset that the universe has outgrown. As we look across the landscape of modern physics in 2026, the old boundaries are falling everywhere. The clear lines that once separated space from time, matter from information, and the observer from the observed have been washed away by a tide of precision data. We are standing in the ruins of the Newtonian clockwork, looking out at a cosmos that is far more mysterious, fluid, and participatory than anything our ancestors imagined. It is a world where a millimeter is a vast landscape of changing temporal currents, where an electron is an undecided traveler choosing multiple histories at once, and where the total universe sits in a silent, static, magnificent monument of pure potential, waiting for an internal participant to give it a name and a direction. This realization does not diminish the human story. It elevates it to a staggering tier of responsibility. We can no longer hide behind the excuse that we are small, insignificant bystanders in a vast, indifferent cosmos. We are the authors of its history. We are the ones who take the silent, timeless architecture of the underlying equations and translate it into a world of color, movement, memory, and hope. The arrow of time does not carry us along like sticks in a river. We are the current itself. The 19th decimal place did not expose a mistake in our calculations. It exposed the true depth of our signature written onto the fabric of reality. The clock is ticking because we refuse to stop looking, because we refuse to stop remembering, and because we are still deeply, beautifully entangled with the mystery of everything that is. This deep entanglement between the act of looking and the thing seen forces us to completely redesign the framework of human knowledge. For generations, the holy grail of physical science was the pursuit of an objective reality that remained perfectly stable regardless of whether an intellect was present to perceive it. We wanted to believe in a world made of hard, predictable stones that fell at exact speeds through a passive, unbothered dark. But as our clocks pierce through the 19th decimal place, they reveal that the very qualities we assigned to those hard stones, their position, their speed, and the steady duration of their fall, are not native properties of the matter itself. They are the structural artifacts of a continuous, high-volume negotiation. Reality is not a gallery of objects. It is a long, uninterrupted conversation, and we are not merely listening to the words. We are actively helping to write the script. This relational revolution requires a new way of looking at our own history as a species. We used to view our cultural evolution as a journey toward an increasingly accurate map of an external wilderness. We thought our ancestors were simply wrong about the architecture of the cosmos, confusing their local mythologies with objective truths, while we were steadily uncovering the real, unbiased mechanics of nature. But if time and causality are emergent, perspective-driven phenomena, then our ancestors weren't necessarily wrong. They were simply operating within a different tier of informational entanglement. When humans lived in smaller communities, without global communication networks or high-resolution instruments, their local environments were less audited by a collective web of data. The consensus of their classical reality was constructed out of a different volume of transactions by building a globally interconnected technological network, by wrapping the planet in fiber optic cables, filling the skies with thousands of GPS satellites, and monitoring every square inch of the surface with digital sensors. We have artificially amplified the decoherence rate of our region of space. We have driven the consensus of our classical reality to an unprecedented level of rigidity. The reason the world looks so hyperdeterministic, cold, and mechanical to us today is not because it was always that way. It is because we have built a technological surveillance system so vast and relentless that it forces every quantum possibility to collapse into a sharp, singular history the moment it manifests. We have engineered the very cage of time we find ourselves trapped in. This loop of measurement and solidification becomes strikingly apparent when we trace the path of our finest instruments into the subatomic dark. When a physicist isolates an atom in a vacuum chamber, they are attempting to create an artificial pocket of historical innocence. They are trying to build a tiny sanctuary where the universe is temporarily relieved of the burden of keeping a record of itself. Within that clean, isolated space, the particle is free to explore all its possible identities at once. It can exist in multiple locations simultaneously, travel down contradictory paths at the same time, and live through a superposed state where before and after are completely indistinguishable. It returns to the true, primal, timeless baseline of the cosmos. But the tragedy of our curiosity is that we cannot bear to leave that innocence unmolested. We want to know what the particle is doing. We want to verify our equations, test our models, and claim our discoveries. So we open a window into the sanctuary. We fire a laser pulse, trigger a detector, or read a clock display, and the exact instant our macroscopic infrastructure touches that isolated system, the pocket of innocence shatters. The universe demands its thermodynamic tax. Millions of bits of raw quantum information instantly leak out into the surrounding wires, computers, and brains, becoming scattered among trillions of particles in an irreversible cascade of disorder. The superposition collapses, the fluid probabilities harden into a single concrete datum, and the particle is violently dragged back into the linear, one-way highway of macro time. Our knowledge is bought with the destruction of the system's freedom. This trade-off is the central unacknowledged economy of the modern scientific enterprise. We are like explorers who can only map a pristine forest by cutting down the trees to make room for our transit lines. Every time we push our diagnostic tools to a higher tier of decimal resolution, we are not just refining our measurements, we are increasing the thermodynamic cost of our existence. We are forcing the universe to burn through its store of low-entropy order at a faster pace, expanding the boundary of historical certainty at the expense of our long-term environmental stability. The 19-decimal clock at the National Institute of Standards and Technology is an exquisite monument to this paradox. It is an instrument that achieves unprecedented accuracy by imposing an unprecedented level of informational violence on the atoms it pins in place. If we follow this perspective to its logical edge, it completely upends our understanding of cosmic entropy and the ultimate fate of the universe. Traditional thermodynamics warns us that the cosmos is on a slow, one-way march toward a state of total disorder known as heat death. According to this model, every star that burns, every engine that turns, and every chemical reaction that occurs contributes to a steady, irreversible rise in global entropy. Eventually, trillions of years from now, all the usable energy in the universe will be completely exhausted, leaving behind nothing but a cold, uniform, lifeless soup of spent radiation where nothing can ever happen again. This is the ultimate, depressing conclusion of a physics that treats time as an objective highway leading from a structured past to a chaotic future. But if the arrow of time is an artifact of the observer rather than a fundamental law of matter, if entropy is simply the measure of how much information is leaked out into our local environment, then heat death is not a universal destiny. It is a local horizon. It is the limit of our specific informational relationship with the cosmos. The universe as a whole, described by the timeless Wheeler-DeWitt equation, does not possess a total entropy that can rise or fall. It just exists as a static, multidimensional landscape of pure potential. What we call the rise of entropy is merely our path through that landscape, the track of our own increasing entanglement with the surrounding world. Heat death isn't the universe running out of fuel, it is the observer running out of perspective. It is the moment where our local system has become so deeply and thoroughly entangled with everything else that there are no longer any unmeasured, uncertain relationships left to explore. The timeline doesn't end because the cosmos dies. It ends because the story has been completely told. This relational framework changes how we should approach the deep mysteries of quantum gravity and the search for a unified theory. For over a century, the best minds in science have been locked in a bitter struggle to find a single mathematical language that can bridge the cosmic scale of general relativity and the subatomic scale of quantum mechanics. We built massive supercomputers, filled blackboards with complex string theory formulas, and proposed radical ideas like extra hidden dimensions and microscopic loops of space. Yet, every attempt to force the two frameworks into a single package has resulted in mathematical nonsense, producing infinities and contractions that defy explanation. The reason for this century-long failure becomes clear the moment we look at the role of time in both systems. We were trying to merge two theories that are built on completely incompatible definitions of duration. General relativity treats time as a flexible, dynamic participant that bends and warps alongside space, responding directly to the presence of mass. Quantum mechanics treats time as a rigid, external parameter that sits outside the system, ticking away at a steady, uniform pace, like an unmovable clock on a laboratory wall. Trying to combine them without changing our vocabulary is like trying to build a house using bricks that are simultaneously solid stone and fluid water. The problem isn't that our equations are missing a piece. The problem is that we are trying to use a tool, the concept of global, independent time, that does not exist at the level of reality we are trying to map. To move forward, we must find the courage to abandon the concept of time at the fundamental level of our equations. We must learn to write the laws of nature in a language that is completely timeless, a language where things do not evolve over an independent duration, but instead change relative to one another through local, direct transactions. We don't need a theory of quantum gravity that explains how space-time changes over time. We need a theory that explains how the appearance of space-time bubbles up from a timeless network of quantum correlations. We need to stop asking how the clock ticks and start asking how our relationship with matter builds the clock in the first place. This shift in focus brings a striking clarity to the experimental anomalies that traditional physics has spent decades trying to ignore. Think back to the small discrepancies noted by Haffel and Keating during their famous round-the-world flight in 1971. While the main result perfectly confirmed Einstein's predictions of time dilation, the actual data contained tiny, persistent variations that didn't quite sit flush with a smooth, geometric model of spacetime. For decades, these variations were quietly dismissed as experimental noise, minor tracking errors, or the result of imperfect atmospheric conditions. But when you view those flights through a relational lens, those discrepancies look less like noise and more like the signal. They are the subtle, irregular tremors of a temporal network that is constructed out of localized transactions rather than a smooth, continuous fabric. The clocks didn't just respond to altitude and velocity. They responded to the specific, chaotic density of information they were interacting with along their path. The same reframing applies to the dizzying results of the 2021 Colorado experiment, where time was observed to change its pace across the thickness of a single millimeter. In a traditional relativistic framework, that millimeter scale variation is treated as a triumph of Einstein's genius, a proof that his field equations hold true even down to the scale of human consumer electronics. But if you stop and think about the weight of that result, it becomes a conceptual nightmare for the traditional model. If time changes its stride across a millimeter, then there is no such thing as a single, uniform object called a particle. A particle is an entity that occupies space, which means it has an extension. If the top of a particle is aging at a different rate than the bottom of that same particle, then the particle is actively tearing itself apart along its own internal timeline every single microsecond. It is living through a state of permanent temporal shear. The only way to rescue the stability of the world from this internal temporal shredding is to accept that the particle does not exist within a smooth, pre-existing space and time. The particle is a localized knot of information exchange, and the space and time it appears to inhabit are the averaged out, statistical concepts that emerge when we measure that knot from the outside. The millimeter gradient isn't a distortion of a real physical fabric. It is the measure of how our own diagnostic tools slice up an underlying network of relational dependencies. This brings us to a deep philosophical realization about the true nature of our scientific progress. We like to think that our technology is a tool for revealing the objective truth of the cosmos, a ladder that lifts us above the distortions of our human biology so we can look at the unvarnished machinery of nature. But our most precise experiments are showing us that our technology is not an escape from our perspective. It is an amplification of it. The more sensitive our instruments become, the more they hold a mirror up to the specific information processing choices that define our consciousness. We built 19 decimal clocks to track the universe, and we ended up capturing the heartbeat of our own methodology. This loop of self-discovery is the real reason why the results from our latest experiments don't add up within the old framework. They don't add up because we are trying to calculate a world that doesn't contain us, while using instruments that are entirely made of our choices. The drift of the constants, the superposition of causal sequences, the timelessness of the total cosmos, and the relational generation of duration are not separate, isolated puzzles waiting for clever technical fixes. They are the collective symptoms of a profound paradigm shift that is forcing us to grow past the primitive, mechanical worldviews of the past. We are living through the exact moment in human history where the training wheels of objective materialism are coming off. It is an uncomfortable, dizzying transition because it strips us of the ancient comfort that the universe is a solid, ready-made home that will take care of itself regardless of our actions. It hands the responsibility for the structure of reality directly back to us. It tells us that the world we inhabit, the world of stable histories, predictable sequences, and reliable causes and effects, is a reality that we must actively maintain through our continuous, disciplined engagement with information. As we look out into the future toward the next generation of deep space missions, quantum laboratories, and hyper-precise instruments, we must learn to operate with a new kind of scientific maturity. We must stop demanding that the universe conform to our simple, linear stories, and instead learn to listen to the complex, multidimensional language it is speaking at the 19 decimal baseline. We must find the wonder in a reality where time is a local relationship, history is a fluid network of potential. And the ultimate truth of the cosmos is not a hidden formula waiting to be unraveled, but a living, evolving connection that we are actively manufacturing with every observation we log, every memory we treasure, and every fraction of a tick we choose to calculate. The clock is not our master. It is our shadow, and it will continue to move across the landscape of existence exactly as fast as we choose to walk into the mystery. This shadow we cast across reality grows longer and more complex the further we push our instruments into the silent corners of the cosmos. If time is not a pre-existing river but the thermodynamic exhaust of our own cognitive architecture, then our entire relationship with the universe must be reevaluated from the ground up. We are used to thinking of ourselves as latecomers to an ancient cosmic theater, tiny biological anomalies that materialized on a speck of dust billions of years after the main scenery was built and the plot was set. But if the linear sequence of history requires an information processing node to collapse its superpositions and anchor its events, then the vast stretches of pre-biological time we find written in the geological strata of planets and the deep light of distant nebulae are not an objective record of what happened in our absence. They are a retrospective reconstruction, a massive, cohesive backstory that our modern interactions are continuously generating to justify the stable classical reality we occupy today. This does not mean the past is a hallucination or a subjective fantasy. The rocks beneath our feet are real, the fossils are physical, and the light from ancient stars is genuinely striking our detectors. But the specific qualities we assign to those artifacts, The definitive assertion that a particular layer of sediment was deposited exactly 400 million years ago on a linear timeline is a macroscopic translation. It is an interpretation that our brains extract from a deeply entangled informational network. The past exists because it is structurally required to hold up the ceiling of the present. It is the architectural foundation that our relational observations continuously reinforce to ensure that when you wake up tomorrow morning, the walls of your house are still standing, the air is still breathable, and the rules of chemistry have not mutated overnight. This systemic reinforcement is what traditional physics has been misinterpreting as the objective stability of nature. We looked at the world and thought its rules were written in steel, but they are actually written in a hyperdense web of continuous mutual confirmation. Every atom in your body is locked in an unrelenting, silent pact with every atom in the chair you are sitting on, the air you are breathing, and the distant horizon you are looking toward. They are constantly checking each other's homework, updating their states, and logging their positions to maintain the macroscopic illusion of a single coherent timeline. The Seco decimal clock at the National Institute of Standards and Technology didn't discover a flaw in this pact. It simply managed to achieve a level of resolution so exquisite that it caught the universe in the middle of updating its ledger. It caught the tiny, fluid adjustments that occur before the consensus settles into a hard, classical fact. This forces us to confront a terrifyingly beautiful possibility regarding the evolution of life itself. In our traditional biological textbooks, life is described as a passive mechanism shaped by the brutal pressures of an external environment. Mutations occur randomly, the environment acts as a sieve, and those organisms that happen to possess the traits necessary for survival pass on their genetic code. The environment is the author, life is just the text being edited. But if the thermodynamic arrow of time is generated by the process of information extraction and memory formation, then the relationship is entirely reversed. Life is not a product of the environment is a creation of life. Consider what a living organism actually is at its deepest physical level. It is a highly organized, localized pocket of low entropy that fights a continuous, desperate war against the disorder of the surrounding world. To maintain its internal structure, to keep from dissolving into the chaotic background soup of nature, an organism must constantly absorb energy from its surroundings, process it, extract information, and discard the resulting waste as entropy and heat. It must build a memory, whether that memory is written in the chemical sequences of DNA, the neural networks of a brain, or the structural design of a cell membrane. Life is, by definition, a specialized apparatus designed to process information and store records of its interactions. Therefore, the appearance of the first primitive life forms on Earth was not an accidental chemical event that occurred within a pre-existing stream of time. It was the moment the arrow of time itself became locked into our sector of the cosmos. Before life materialized, the planet existed in a fluid, symmetric, unaudited state of pure quantum potential, an eternal present where things happened but nothing passed. The moment a primitive cell began to process data to store a record of its environment to ensure its own survival, it acted as a tiny thermodynamic piston. It began to pump entropy into its surroundings, drawing the very first thin, fragile line between yesterday and tomorrow. As life multiplied, diversified, and grew more complex, that line thickened into a highway. The evolution of consciousness was the evolution of historical resolution. We didn't evolve to survive inside time. We evolved to manufacture time as a survival strategy. This biological generation of duration helps explain the profound, vertiginous mystery of the anthropic principle. The long-standing observation that the fundamental constants of nature seem to be exquisitely fine-tuned to allow the existence of conscious life. If the strength of gravity, the mass of the electron, or the fine structure constant were altered by even a fraction of a percentage point, stars would never have formed, atoms would fly apart, and the complex chemistry required for living organisms would be completely impossible. For decades, scientists have puzzled over this improbable fortuity, wondering if we live in a massive multiverse where trillions of sterile universes are born and die, and we simply happen to inhabit the one lucky reality that struck the jackpot. But the relational universe eliminates the need for this desperate speculative multiverse. The constants of nature look perfectly tuned for life because life is the entity that is actively stabilizing those constants through its continuous observations. The fine tuning isn't a cosmic coincidence that occurred before we arrived, it is an ongoing structural requirement of our perspective. The numbers hold together precisely because we are looking at them. The 19th decimal clock detected a drift in those numbers because our technology is beginning to push beyond the biological boundaries of our information processing needs. We are demanding a level of precision that our biological evolution never required to maintain our survival. And at that extreme edge, the universe is showing us that its rules are not a rigid cage, but a flexible canvas that yields under the weight of our relentless interrogation. This brings a stark, immediate significance to the work being conducted in quantum laboratories across the globe as we move through 2026. When we see researchers placing causal sequences into superpositions or erasing the arrow of time within microscopic circuits, we are not looking at trivial academic exercises. We are looking at the first tentative steps of a species that is learning to domesticate the fundamental fabric of reality. We are like primitive humans discovering fire, staring into the flames of a force that we do not yet fully understand, fascinated by its power, but terrified of what it implies about the world we thought we knew. If we can manage to scale these technologies, if we can build macroscopic systems that operate within the timeless, relational framework of pure information, the consequences will completely transform our civilization. We will no longer be restricted to building tools that react to events after they occur. We will learn to construct systems that navigate the multidimensional landscape of potential before it solidifies into a single timeline. We could design communication networks that transmit data across relational coordinates rather than spatial distances, bypassing the limits of geography and the speed of light entirely. We could engineer computing systems that solve problems by allowing future outcomes to retroactively shape past parameters, turning the entire concept of engineering inside out. But this technological dream carries a heavy existential warning. If our reality is stabilized by the collective consensus of our information exchange, then our modern obsession with digital distortion, synthetic data, and fractured communication networks is an architectural threat to the world we inhabit. We are currently building platforms that flood our collective consciousness with contradictory signals, automated noise, and simulated realities. We are breaking the shared narrative of human experience into millions of isolated, conflicting echo chambers, each one operating on its own private set of facts and memories. In a purely mechanical universe, this informational chaos would be a tragedy of human culture, a dark age of politics and sociology. But the hard rocks of nature would remain completely unaffected. The stars would still shine, the planets would still orbit, and the laws of physics would keep marching on, indifferent to our confusion. But in a relational universe, where the stability of classical reality is maintained by the consensus of its participants, an informational civil war is an environmental catastrophe. By shattering our collective memory, by destroying the shared baseline of our observations, we are loosening the structural rivets that hold our timeline together. We are introducing a dangerous, unpredictable volatility into the local matrix of reality. The drift caught by our finest atomic clocks might not just be a symptom of our high-precision technology. It could be the first structural warning sign of a cosmos that is beginning to wobble because its observers have forgotten how to agree on what they are seeing. This realization forces us to approach the enterprise of science not with the arrogant desire to conquer an external wilderness, but with the profound protective care of an architect maintaining a sacred temple. We must recognize that our instruments are not passive windows, our equations are not clean summaries of an external truth, and our lives are not insignificant accidents. We are the active custodians of the cosmic timeline. The 19 decimal places of the NIST clock are not a boundary line that separates us from a cold mechanical infinity. They are an invitation to wake up to the true scale of our participation in the creation of everything. The universe is not a clock that is running down its spring toward an inevitable icy death. It is a living, breathing relation, an infinite field of entangled potential that has spent 13.8 billion years learning how to tick through us. And the direction it moves from here is not written in the stars, or hidden in the equations, or locked away in a distant past. It is being decided right now within the quiet thermodynamic heat of your own mind as you choose how to remember where you have been and how to look toward the unwritten horizon that is waiting for your gaze to bring it to life.